Let's take a second to review what we know about symmetric functions and trace evaluations and compare and contrast. So let's let W in Sn avoid the patterns 3, 4, 1, 2, 4, 2, 3, 1. And let's let mu and lambda be partitions of n. So first of all, the coefficient of m mu, the monomial symmetric function m mu, in the elementary symmetric function E lambda is the number of column strict Young tableau of shape lambda transpose and content mu. Now E lambda is the Frobenius characteristic of the induced sign character. And if we evaluate the induced sign character at the Cauchy-Analytic basis element indexed by W, then this is the number of column strict PFW tableau. Of shape lambda transpose. So it's almost the same. So column strict here meant less than in the integers, and that turned into less than in a poset. Alright, similarly the coefficient of m mu in H lambda is the number of row semi-strict Young tableau of shape lambda and content mu. So content mu means mu1 1s, mu2 2s, mu3 3s, etc. H lambda is the Frobenius characteristic of the induced trivial character, eta lambda. And eta lambda, evaluated at the Cauchy-Analytic basis element CW, is the number of row semi-strict PFW tableau of shape lambda. So what was less than or equal to in the integers, so here row semi-strict means as we go to the right, integers increase or stay the same. That became less than in the poset or incomparable in the poset. So less than or equal to became less than or incomparable to. Alright, we have a couple more bases to go through. The coefficient of m mu in the Schur function S lambda is the number of standard Young tableau of shape lambda and content mu. Standard means column strict and row semi-strict. Now the Schur function is the Frobenius characteristic of the irreducible character chi lambda. And when we apply chi lambda to the Cauchy-Delistic basis element CW, we get the number of standard PFW tableau of shape lambda. So now less than in increasing in columns is part of standard, and that becomes increasing in the post set, and then weakly increasing in rows, which is less than or equal to as integers, becomes less than in the post set or incomparable in the post set. So just like the combination of elementary symmetric functions and homogeneous symmetric functions, or induced sign characters and induced trivial characters. Alright, now let's look at the power sum basis. The coefficient of mu in the power sum p lambda is the number of row constant Young tableau of shape lambda and content mu. Now the power sum is the Frobenius characteristic of the power sum trace. And when we apply the power sum trace to a Cauchy-Delistic basis element, we have a couple of things we get. So we get the number of cylindrical FW tableau of shape lambda. We get the number of cyclically row semi-strict F tableau of shape lambda. And we also get the number of record-free row semi-strict F tableau of shape lambda. So here, in a column, row constant means you get the same number all the way across. So equal in the integers now becomes, well, one path leads to another path, or one path starts where the last one left off, and then connects around at the beginning again. So we have this connected paths, and they loop around and finish where they started. Which is kind of like the last one in a row being equal to the first one in a row. Or cyclically row semi-strict. So we have equality becoming less than in the post set or incomparable to. And then that also has to hold at the end to the beginning. And then with a record-free semi-strict tableau, equality becomes no greater than anything we've seen so far. So the above, because it's row semi-strict, plus no greater than what we've seen so far. So in terms of pictures, there is some connection between how we expand symmetric functions in the monomial basis and how we evaluate the corresponding traces at Kajdan-Lustig basis elements. So these are 4 families of traces corresponding to 4 families of symmetric functions. And we still don't know what is the monomial trace evaluated at a Kajdan-Lustig basis element. And we don't even know if it's greater than or equal to 0, but we think it is. So well, we could sort of proceed as we did before. The coefficient of m mu in m lambda is, except that if we proceed as before, we're not going to get a lot of distance, because this is a basis. So the coefficient of one basis element in the basis is just 1 if these are the same basis element and 0 otherwise. So we don't have a combinatorial interpretation of tableau really that is going to lend itself to decide to conjecturing a tableau interpretation of the monomial trace evaluations. But I'd still say, I mean, if this is non-negative, this must be the number of FW tableau of shape lambda with some property. Because it just worked, it worked for all of the other bases. So if this thing is non-negative at all, my feeling is that it has to have that form. So we have a partial result. The Stembridge proved this. If lambda equals, I'll write m to the k, and I mean all the parts are equal to m, so let's say there's k parts equal to m, which means that if lambda is a partition of n, then n, I guess, has to be m times k. Then the evaluation of the monomial trace at this Kajdan-Lustig basis element is the number of column strict cylindrical PFW tableau of shape m to the k. So let's do an example of that just to see what it looks like. So let's let W be 2, 3, 4, 1, so that FW equals this picture. And let's let lambda be 2, 2. So we want to put paths in tableau of shape 2, 2 so that it's cylindrical. So one path starts where the last one ends, and the first one starts where the very last path in the row ends. And they have to be column strict also. So this path can't touch that path. It has to be entirely below it. And this path has to be entirely below that path. So it looks like if we're going to make a tableau like this, probably we're going to use sources and sinks 1 and 2 in the first row, and then sources and sinks 3 and 4 in the second row. So we could have this cycle in the first row. So 1 goes to 2, 2 goes to 1. And then maybe 3 goes to 4, 4 goes to 3. Only problem is when 4 goes to 3, it hits that vertex, which when 2 goes to 1, it also hits that vertex. So this isn't exactly right. But if we switch these paths on top, when 1 goes to 2, it doesn't hit 4 going to 3, because 1 goes to 2 doesn't go that high. And then when 3 goes to 4, it doesn't intersect 2 going to 1, because 2 going to 1 only goes as high as this vertex, but 3 going to 4 is above that. So there's 1. And then we can swap the two columns. So we'll still have the cylindrical property in each row, and we'll still have column strictness. So we can have 2, 1, 1, 2, 3, 4, 4, 3 in a tableau like this. And so in this case, we have, now those are the only two. We have that the 2, 2 monomial trace evaluated at the Kajdan-Lustig basis element C, 2, 3, 4, 1 equals 2. And this rule doesn't work for non-rectangular shapes. And for n less than or equal to 5, it always seems to give an answer that's too low. Well, sometimes it's actually correct, but for instance, when we have rectangular shape, it's going to be correct. So it's either correct or too low. So it's less than or equal to. Less than or equal to what we're trying to find an interpretation of. But I guess that's sort of good, because if we're trying to prove that this is non-negative and we find something else that's less than it and is still non-negative, well, greater than non-negative is non-negative. Although we'd still have to prove that. So it's open to show that this is greater than or equal to the Stambridge rule applied to all shapes. And there's some special cases of Stambridge's rule that we've already seen. So if that rectangular shape is a tall, skinny rectangle that has, it's only one box wide and n boxes high, then that monomial trace is just the induced sign character, since the monomial symmetric function m sub 1 to the n equals the elementary symmetric function en. And this counts column strict tableau of shape 1 to the n. So these are automatically going to be cylindrical because every path, well, the path in position I is going to start at source I and end at sink I. And then another special case is phi to the n. So phi to the n applied to a Cauchy-Johnlistic basis element equals psi to the n applied to the same basis element. And we know one of these interpretations is the number of cylindrical FW tableau of shape n. Now this is true since the monomial symmetric function mn equals the power sum symmetric function pn. Now if we think about what these tableaux look like, they're shape n. If it's cylindrical, then, well, it's cylindrical in rows. So every path starts where the previous one ended. The last path ends where the first path starts. And this is automatically column strict because there's never two paths in a column. Now, I would love to, and a lot of people would love to have a formula for what phi lambda of a Cauchy-Johnlistic basis element is. It's open for q equal to 1, it's open for general n, it's open for W avoiding 3412 and 4231, it's open for W avoiding 312. It's known if all of the parts of lambda are 2 or less. And it's known if lambda is a rectangular shape. So if all the parts are 2 or less, let's look at that. So we have a partition it looks something like that. And then phi lambda of CW is the number of column strict p tableau of shape lambda if the elements of P can't be placed into a tableau with fewer 2's. With fewer rows having 2 boxes. So suppose we can put the elements of P into a tableau, a column strict tableau like this, but we could not put them into a column strict tableau like that. Then we count them. But if we can put them into a column strict tableau like this, and we can also put them into a column strict tableau like that, then phi 2, 2, 2, 2, 1, 1 is going to be 0. Because it has to be the skinniest tableau that the post-it elements can be placed into. The similar result for parts of lambda less than or equal to 3 does not hold. So I'm not sure how much this result is going to generalize. The end.